Okay, folks, glad to have you back. In this screencast, we're going to talk about divisibility tests, but only a couple, and only about what divisibility tests are generally, because we're not very concerned about each and every test in this screencast. You can take the principles and apply them broadly, and that's kind of the hope here. The thing I want to establish for us is that a positive integer z is divisible by a positive integer n if and only if, and remember that every time we see these words, we're about to define what it means for z to be divisible by n. That's what we're defining in this moment. If and only if z is equivalent to 0 mod n, and I am deliberately using language you're familiar with from Math 239. If z is equivalent to 0 mod n, we say that z is divisible by n, and vice versa. Okay? So if I can hit us with a lemma that will be somewhat helpful. If a is equivalent to 0 mod n, then a to the kth power is equivalent to 0 mod n for all natural numbers k. For all natural numbers k. And we're going to do this by induction. Again, something you are familiar with from Math 239. We're going to deliver this by induction. The base case is the case where n equals 1, and I'm just going to argue that that's easy. If k is 1, well, it kind of follows. So let's take the inductive step. In the inductive step, we assume that a is equivalent to 0 mod n, and we assume that a to the k is equivalent to 0 mod n. We will show that a to the k plus 1 is equivalent to 0 mod n. And there's a bunch of you saying, duh, you multiply, but it's not quite that simple. By hypothesis, a is equivalent to 0 mod n, so a is some multiple of n, and a to the k is equivalent to 0 mod n, which means a to the k is some multiple of n. P and q are integers, therefore a to the k plus 1 is a times a to the k is some integer times n, and because a to the k plus 1 is some integer times n, we conclude that a to the k plus 1 is that is just hideously poorly written. So sorry, folks at home. A to the k plus 1 is equivalent to 0 mod n as needed. Why do we need that? Because we're going to take a look at the divisibility test for 3. And in the divisibility test for 3, so you know that a number is divisible by 3 if the digit sum is divisible by 3, right? That's the test for divisibility by 3. We know that if the sum of the digits is divisible by 3, then the number is divisible by 3, and vice versa. How do we make that argument? Well, we know that whatever the number is, it's got some decimal representation. There are thousands digits and 10,000s digits and so on, but there's also a hundreds digit and it's in the hundreds place, and there's a tens digit and it's in the tens place, and there's a units digit and it's in the units place. The argument here says that n is equivalent to all those digits plus h plus t plus u mod 3. That's the argument. Why? Well, 1 mod 3 is equivalent to 10 mod 3, right? I mean, you just add a multiple of 3 to get from one to the other. And because 10 is the same as 1 mod 3, so is 10 to every power. So this is 1 mod 3, this is 1 mod 3, 1,000 is 1 mod 3, 10,000 is 1 mod 3, and you just multiply by 1 all the way down, and you get the sum of the digits. And so if the sum of the digits is a multiple of 3, so is the original number. It's a number theoretic argument that doesn't have to do any hand waving. We can use the lemma and our knowledge of mods to reduce n to the sum of its digits. Similarly, the test for 11. The test for 11 talks about the alternating digit sum being divisible by 11. If the alternating digit sum is divisible by 11, so is the number, meaning we take every digit and subtract out every other digit. So how does that work in this case? Well, you have some number, and eventually it's got a thousands digit, and it's got a hundreds digit, and it's got a tens digit, and it's got a units digit, right? Like you've got those in place. Here's the thing. Every other power of 10, like the second, fourth, and so on, all of these are one less than a multiple of 11. But the odd places, all those powers of 10 are one more than a multiple of 11. Why? Because 1 is one more than a multiple of 11. 10 is one less, 100 is one more, 1,000 is one less, and so on. So in a mod argument, n is equivalent to, that's negative 1 mod 11 times t. That's 1 mod 11 times h. That's negative 1 mod 11 times t. That's 1 mod 11 times u. So if the alternating digit sum is a multiple of 11, so is the original number. And so we can establish certain divisibility rules using mods. There are other divisibility rules that we don't want to establish using mods. We'll talk about those when we gather. Hope that this is helpful to you and reminds you of some things you have learned before.